This is PowerPoint 212A, Introduction to Structural Member Properties. We're talking about structural members. We're talking about beams and how they are oriented and how they are used to help support buildings and houses and things like that. We're going to learn how to calculate how these beams are going to deflect, how much weight they can support, how they are going to help us, and how we need to make sure that we're orienting them, and how the price affects how this is going to come into play when we're building things. By the end of this PowerPoint, you should be able to calculate moment of inertia and beam deflection. You're going to hear us talk a lot about that. And you're going to have to understand that structural member properties, including centroid location, moment of inertia, and modulus of elasticity, are important considerations for structural design. When we're talking about structural members, moment of inertia is key to us. Moment of inertia is essentially the stiffness of an object. So if we would look at this diving board here, which we have all probably been on or seen, we know that when we jump on this diving board, there's going to be a spring effect. So the spring effect is going to allow us to push down, and we are going to be able to jump up. So as we push down here, the board is going to flex, and then it's going to push us back up, and then we're going to jump in. So we're going to be jumping out here. Whereas this diving board over here, if you are pushing off of this diving board at this location, it's going to be a lot stiffer. So it's going to not flex nearly as much. In fact, you probably wouldn't feel it flex at all. So when you do, if you're standing here, you're pushing down, you're going to be jumping out this way into the pool as if you are starting a race. So most of us have been on the diving board on the left. We can understand how that feels. So in general, a higher moment of inertia produces a greater resistance to deformation. So we're going to look at why some of these boards will flex more or flex less depending on what they're made of and how they are turned. So how does moment of inertia help us? What is it going to do? How is it going to make a difference to us in our lives? It's very simple, actually. When you look at these two different boards, so if you look at these boards up here, they're the same board. One of them is just turned on their side. So up here, we're going to call this beam A. So notice how it's located on its side. We're going to look at this portion here, and then beam B is the exact same board. It's just turned, laying down side by side. Beam A is made out of Douglas fir. This is just a basic 2x6 board. If you go to the hardware store and ask for a 2x6, typically it's going to be a pine board. Pine is relatively cheap because it grows fast. Pine trees are reproduced a lot quicker than what we call a hard wood tree. So a pine tree is something that bears cones or needles, whereas a hardwood tree, something like an oak or a maple tree, is leaf bearing. So you learn the difference between our deciduous and coniferous tree as well. So if you look at the actual size here, I call this a 2x6. The real size of these boards when they come out are not 2x6. They're actually only 1.5 inches by 5.5 inches. That's just all depending on how the board has been brought down and cut down into that specific size. So again, when you actually go to buy these boards, they're not really a 2 inch by 6 inch true size. If you would actually measure it out, it would be 1.5 inches by 5.5. Most of the time you're going to come in 8-foot lengths. So as we see here, we're just going to call this thing 8 feet. And if you would change that into inches, 8 feet multiplied by 12 inches, that's going to give us 96 inches. That's going to be important to us later on in this slideshow. But as you look here, beam A, the length is 8 feet. The width now here this width is only 1.5 inches. Whereas the height from here to here, this is 5.5 inches. When we flip it and we call it beam B, now our width from here to here, that's 5.5. Whereas our height now is only 1.5 inches. That's going to come into play later on in the PowerPoint. Area is not going to change. Area for a square object or rectangular object is just going to simply be base times height. So as you can see, same thing, 5.5 times 1.5 or 1.5 times 5.5 is still going to come up to our 8.25 square inches. So what's going to distinguish this? What's going to make beam A and beam B different? So what we are doing is the yellow arrows are going to symbolize a load or a weight. So when you have resistance in the board, if you apply weight and pressure, notice how the weight is applied up here on beam A, how much deflection it has. It does not deflect nearly as much. If you look really close in this area here, as the animation goes on, you can see how much it deflected. Or if you look in beam B, same thing here, the load is applied, look at the difference in the actual flex. So it does deflect quite a bit more. You have a lot bit more flexion. So beam A and beam B, they're made out of the exact same boards, and the only difference is how they're actually just turned. So this beam B is going to flex quite a bit more than beam A. Up. If we look here at what these things mean, we've got this IXX. This IXX is actually moment of inertia. So what that IXX stands for is this moment of inertia, which we're going to be calculating for. The B and the H, the B is going to be your base, and the H is going to be your height. So if you look at the board, if you turn it on its side, if you just look at it as a rectangle, you can look at the base and get your base number here, your height number here. So all you're going to do is just plug those in. So moment of inertia equals base times height cubed divided by 12. 12 is going to represent 12 inches. So when you go through and actually start calculating moment of inertia, if you're calculating moment of inertia for beam A, this is when we turned our beam on the side. So when our beam was turned on the side here, we have a base of 1.5 inches and a height of 5.5 inches. So we would just simply take and plug this number in here. Our base is going to go in here. Our height is going to come in here. We'll calculate it out. Our substitutions. What we have here, our answer is 21 inches to the 4th power. So if you are given a problem that said, please calculate moment of inertia for this particular board, with it being 5.5 inches for the height and 1.5 inches for the base, my number is going to come out to 21 inches to the 4th. So we're going to take the exact same board here, and what we will do is we'll just kind of take and we're going to turn it on its side, and we're going to look at how the moment of inertia is going to come out differently when we substitute our 5.5 inches here for our base, and our 1.5 inches now is going to be our height. So as again we turn it over, this is our base and this is our height. From here to here's base, here's height. So we go through and we start plugging in our numbers. Our 5.5 inches multiplied by our 1.5 inches cubed divided by 12, we are going to come up with a moment of inertia for beam B as 1.5 inches to the 4th power. So if you look at the two boards, it's actually the exact same board, just turned on its side. The numbers of the moment of inertia are completely different. So as these two numbers are put on the screen here, as you watch the animation, on the top one, beam A is getting the same amount of pressure as beam B. So the moment of inertia for beam A is this 21 inches to the 4th power. The moment of inertia for beam B is this 1.5 inches to the 4th. This pressure and this pressure are the same. So we're not cheating here. We're not saying this beam is getting a lot more pressure. They're both applied the same amount of pressure. So you can see how much more the beam deflects. Where this is going to help us in engineering is essentially how we orient and turn each one of these boards. It's the exact same board, but look at how much different, look at how much stronger the board A seems to be compared to beam B in this case. And again, we mathematically just calculated that it is stronger when you turn it on its side. So if you compare 21 in the 4th, or excuse me, 21 inches to the 4th and 1.5 inches to the 4th, this beam up here, beam A, is 14 times stiffer than if the beam was turned on its side to be beam B. When we start talking about different beams, when we have in engineering, there's a lot of different types of beam shapes. So we've got just a solid bar here. This is an L here. This is what we call a C channel. And this one down here, this is the I-beam. So this is the one that you could probably see in your basement if your basement is unfinished. This one over here is a tube. So if you go look in your basement and you see a big beam running across the bottom of your floor, that would be on the roof in the basement, that's your I-beam. Those things have to be really strong. We want to make sure that our house isn't going to fall down. So as engineers, we need to figure out now which one of these beams is going to be the best suited for each particular case. So if we look at two structures here, what we're going to do is we're going to apply some values. So these values are just given. So Project Lead the Way made these values up and they gave them to us. And they said, okay, this moment of inertia for this beam, this is a non-composite versus a composite beam. The moment of inertia for this beam is 10.67 inches to the 4th with an area of 8 inches. This beam, moment of inertia is only 6.08 inches, but the area is 2.70 inches. So we're looking at the difference between two beams here. One is typically going to be something from the sawmill, so like this would be maybe more along the lines of like a 2x4 or 2x6. This one over here is going to be engineered or made or manufactured in some way, shape, or form. So it's not natural. We have to put these two things together. And one of the best parts about engineering is when you start putting things together, you can see that you can make things stronger with less material. If you recall here, the centroid, that's what that little symbol is on each one of these beams. So what we're doing here is we're going to look at the amount of area. We're doing more work with less. One other thing that you can compare this to is, what if I changed this? I took this out. If I said this was not composite. Okay, just forget all of that. Just say this is gold. And this is gold. If you look at the amount of area in this one compared to the amount in area in this one, you're going to see that this one has a lot less area, so it's going to be cheaper. So we're saving material and we're doing the same essentially amount of work. Now, of course, when you're building structures and components, you're not going to be building them out of gold. Gold is not as strong as structural members, and obviously it's going to cost a whole lot of money. When we look at these two diving boards, we're going back to the diving board examples, we are going to look at how modulus of elasticity actually represents stiffness. So if you look at the diving board here on the left, so if you climb up this ladder and you get yourself right here, you're way far up in the air. When you go to jump off this thing, you're going to apply pressure here, down, and then you are going to catapult off down into the water and do your flip or whatever it is you're doing. That's fine. There's no problem with that. The only downfall is you have to get a lot higher. This is not going to flex at all compared to this guy. So this guy, we've got these two steps. We're walking ourselves up. We're going to jump up here. We're going to apply the pressure. We all know that when you push down here, you're going to have a spring effect go back up. When you jump up, it's going to push you up. That's where you're going to get your height, and that's when you're going to jump into the water. So the modulus of elasticity deals with the stiffness. So this part right here, if you were trying to relate modulus of elasticity, I would say stiffness and modulus of elasticity are the two words you need to kind of put together. So in general, a higher modulus of elasticity is going to produce a greater resistance to deformation. So this diving board over here, this one is going to have a higher modulus of elasticity, whereas the springy one, this is a lower modulus of elasticity. So if we look at two different boards or two different types of material now, we're going to be calling beam A, we're going to call that Douglas fir again, down in here. A typical softwood board, get from the hardware store. It's going to call out, it's going to typically be called a 2x6. So, and these are in inches, where in reality, that's actually 1.5 inches by 5.5. When we go through and we do our activities and we practice our problems, we're going to just give you these values. So we're going to set these values up for you. Your job is just going to be able to put the values in the correct location. This one up here, beam B, we're going to call this ABS plastic. ABS is just a type of plastic. It's just a different chemical makeup. If you would stop and think about all the different types of plastic in the world, take two examples. A soda bottle and your cell phone case. Both of those are plastic. Both of those are made out of different types of plastic material. You can take the soda bottle and kind of crunch that down, and you can see that it's going to flex back. That modulus of elasticity is going to be different than the modulus of elasticity of your cell phone case. So the ABS is just a different type of plastic. That's the only thing. On this chart here, you are given the length, and remember, 8 feet is the same thing as 96 inches. And we get that from quite simply multiplying 8 feet times 12 inches is going to give us 96 inches. The width is given, 1.5 inches for both materials. The height is 5.5 for both materials. The area, which is width times height, for both materials is 8.25 inches squared for the Douglas fir and for the ABS plastic. So what's going to distinguish? What's going to give us a difference from beam A to beam B? Outside of the common something that you can obviously see. It's very obvious that beam B is a different material. We said this is ABS plastic, and this is a Douglas fir. So this is wood, and this one's plastic. Well, we can obviously tell that there is a difference there, but what's going to distinguish those two? So what we have there is the resistance, the modulus of elasticity. So which one is going to deflect, or have the most flexion in their principles? So if you would put this board and support it here, and support this board here, and apply a load in the middle for both, what we're asking is which one is going to deflect more. So if you apply the same load for the plastic, look at how much farther it is deflecting this distance here to here compared to this one. It's deflecting here to here. Now in the real world, you're probably not going to see it flex quite this much. If you're having this much flexion in your boards, we're probably going to have an issue. But if you're looking at how the structural members are going to support things, you will have some form of deflection. You're not going to always have just a board or a member that doesn't flex at all. You always are going to have to account for things moving and flexing. So we want to know why. Why did beam B have greater deformation than beam A? Well, you could say, well, it's very simple. The one's made out of plastic and the one's made out of wood. But that's not going to really solve our problem, because there are plastics out there and there are composites out there that are actually stronger than wood. There's actually some fiber material that is stronger than steel. If you've heard of carbon fiber, that is actually lighter weight than steel and actually stronger. The downfall is it's more expensive. So what we have to do now is we have to look at the difference in the modulus of elasticity. So we're going to introduce another equation for you. We're going to look at this. This is deflection. So how much the change, the triangle here means how much change in the max. The applied force and the length of the span between the supports. We're going to look at modulus of elasticity and this thing, moment of inertia. So when we go to calculate the beam deflection, we actually need to know how much this thing is going to deflect. So beam deflection, how much is each one, or excuse me, how much are each one of these boards going to flex this way? So we just need to go through and put some numbers to it, because again, in engineering, we want to make sure that we just back our facts up with numbers. The numbers are not going to lie. If we go through and apply the calculations, we're going to be able to justify which board we pick based upon which one deflects more or less. So if we look here, the F in the equation, so our F is going to come from force. So this force is going to be our F. Our L is the length. So this board length for the Douglas fir and for the plastic were both 8 feet long. Our force that we're applying, we're just saying we're putting 250 foot-pounds on each one of these boards. The 48 is a given. So this is a given. This will not change. The moment of inertia and the modulus of elasticity will be different for each of your boards. So on the next slide, we're going to go through and we're actually going to put the numbers to this and see exactly why each board did what it did. So now we're going to calculate. We're just going to go ahead and substitute and solve. For beam A, our force, 250 pounds, is going to go here. That's what this guy is. Our length comes from here. Remember, 8 feet is the same thing as 96 inches. So that's where this part comes into play. 48, this does not change. This is given. 1,800,000 psi. That is the modulus of elasticity. This big number comes from down in here. Again, this is given. You may have to look up the specific type of board that you're going to be calculating, or maybe it's a steel, or maybe it's a different type of plastic. Whatever the type of material is, you may have to go up and reference the modulus of elasticity. It should not change very much from board to board. There will be a slight difference in each particular board. However, it will not change that much based upon the types of material that you have. Our moment of inertia is going to be given here as well. So when you do all that, you calculate it all out. This, I made a mess here, but this beam deflection in board A is 0.12 inches. So if you can't see it, where A equals 0.12 inches. You do the same thing for beam B. You look at your force. Force is 250. Look at your length, 8 feet. Remember, same thing as 96 inches. 48 does not change, so that's given. Your modulus of elasticity for this one is quite a bit lower. You notice on the last one it was 1,800,000. This one's only 419,000. And again, PSI is pounds per square inch. Moment of inertia is 20.80 inches to the fourth power. So we substitute and solve. This particular beam, this beam B that we said was made out of ABS plastic, is going to deflect this 0.53 inches. So what does that mean to us? Beam A and beam B, they're the same size. The boards look the same, obviously made out of different material. Beam A is going to deflect 0.12 inches. Beam B is going to deflect 0.53 inches. So what that says is, if the same weight is applied here and here, beam A is going to deflect 4.24 times less than beam B. What that means to us is beam B is going to be weaker in terms of flexion. Sometimes you want to account for that. Sometimes you want to have more deflection. Sometimes you don't.